Thank you. So this morning, presentation mode.
Hi, sir. Could the presentation be full screen, please?
Yes, I'm trying to figure it out here. I'm a little bit crappy with the technology. I'm kind of very old school. I still use pencil and paper to calculate things.
No worries. It's at the bottom right, next to the minus sign. Bottom right of your screen. Next to the minus sign, a bit to the left.
Okay, great. Thank you. Couldn't have done it on my own. All right, so this morning, we're going to be looking a little bit at soil physical properties. And as Mrs. Harris indicated, you know, the modules today will be a little bit more involved. For this particular module, we're going to be revisiting some high school chemistry, or some elementary chemistry even, a bit of physics and a bit of math. So if those weren't your favorite subjects, I guess you're in the right place. As they say, you know, to overcome your fear, the best thing to do is to tackle the thing head on. So soil physical properties, and the primary objective of this module is to provide an overview of soil physical properties and their importance in controlling soil temperature, soil aeration, root penetration, the movement and retention of water and nutrients, all of which are important to plant growth. And here are a list of the topics that we'll be covering. So we'll be looking at texture, structure, some water energy concepts, fate of incoming water, qualitative description of wetness, soil water loss, enhancing soil drainage, some principles of irrigation, and soil thermal properties. Now, yesterday the question was asked by, I believe, Dr. Clark in her presentation. Where do we get food? What's the source of food? And I believe the answers to that question were varied, right? And so I sometime after that, last night, I decided to put this slide together, which wasn't originally a part of the presentation. And here's an article that I did in the Jamaica Cleaner about 5-6 years ago, thereabout. And it says soils aren't dirt. And then I started kind of scouring around, and I found a few more articles that basically speak to the same thing. A lot of them more recent, 2020, 2021. And it's a whole plethora of things, even in like nature, geographic. And I think, you know, we take for granted the services that soil often provide. You know, there's not much in terms of respect to the ground beneath our feet, so to speak. One of the big things coming out of yesterday was also food security. You know, how do we ensure food security? And I can't remember a part of that discussion being, you know, healthy soils. It might have been said, but I missed it somewhere. But in order to ensure food security, healthy soils, that's the place to start. And I think oftentimes we overlook the importance of soils. And not just in agriculture, but in a whole host of other things. So the ecosystem services that soils provide are probably quantified, you know, in terms of trillions of dollars. So my first real information slide here is really looking at what is soils, or what are soils, the components of soils, and some of the ecosystem services that soils provide. And we see here that by composition, soil is roughly 45% mineral, 5% organic matter, and the remaining 50% is actually shared between water and air, which reside in the pore spaces within the soil. And if we look here to the left, we have the Sustainable Development Goals. And what we see, there are actually 17 goals. And what we see here is probably roughly about 11 to 15 of those goals that are directly related to soils. So in order to attain sustainable development, or to achieve the Sustainable Development Goals, you see that soil is indispensable to that. Additionally, here we are in these workshops focusing on climate change. We talk about mitigation and adaptation. And again, soils form a huge part of that. So carbon sequestration, which one of the main ways of mitigating against climate change. That's a very large function for soils, right? So how do we achieve these things? We achieve these things through a combination of the physical, chemical, and biological properties of soils, right? So all these ecosystem services are provided via those means. Now, this morning, I want to focus a little bit on the physical properties, right, that are pertinent to us here. And we start with the simplest one, which is soil texture. Now, what is texture? Texture basically is the feel of the soil. How does it feel? Is it gravelly? Is it grainy? Is it smooth, etc.? And so there are three primary classes of we have sand, silt, and clay. We often rule out gravel because of the much larger size. You can see here by scale. So of course we know how sand feel, grainy, and that can be of two different courses, two different feel. So there's a fine gravel, and there's a fine sand and a coarse sand. And then of course silt, which is a little bit more smooth, and clay, which is the smallest of them all, a lot smoother. And by definition, there are different standards by which these things are defined in terms of particle size. So essentially the texture is just a measure of particle size, right? And of those three, sand, silt, and clay, what I'd probably like to do is to focus a little bit on clay, with clay being the sort of most reactive of the three different sized particles. And clays are particularly interesting because they confer a lot of properties to soils, both physical and chemical. And so what we have here is essentially a diagrammatic representation of what clays are. So these are layered, what you call aluminosilicate minerals. And they're called aluminosilicate because aluminum is a major component, and silicon is also a major component. So the layers of clays are basically made up of what you call a silicon tetrahedral, which is one silicon atom bonded to 4 oxygen atoms, right, in this sort of formation. And then you have what you call an octahedral layer, which is your aluminum bonded to 8 hydroxide molecules. And then these are stocked together. So we have different types of clay. There's a 1-to-1 clay. So you have one tetrahedral layer, silicon tetrahedral, bonded to 1 octahedral layer. And those 1-to-1 clay, a good example is the kaolin group of clays, or what we call kaolinites. And then we have the more interesting of the clays, which are the 2-to-1 clays, or the swelling clays. So those are the clays that become plastic when wet, they swell, and when they dry, they shrink and crack. So in those 2-to-1 clays, Mount Marillanite, for example, is a well-known example. There's 2 layers of tetrahedron, sandwiching an octahedral, which is what is pictured here, right? And together, these layers make up what you call the basal layer. Now, clays are generally studied using X-ray diffraction, which is shown here. So you might see here this micrograph showing like platy structures. So that is how clays will appear. They're platy because of the stacking. And so this main peak here basically represents all of this, right? Now clays are critical because they are hygroscopic in nature, which means that they take on a lot of water, right? And here we have an infrared spectrum showing clay. And what you can see here is natural water being bonded to the clay. Now, the reason for that is that clays are, because of their very fine nature, they have extremely high surface area. Now, that high surface area lends itself to increased reactivity. But in addition to the high surface area, what you also have is there is this thing in mineralogy that is called isomorphic substitution. And I'll explain what that is. So here we have silicon, right? It has a +4 charge, but this silicon atom can sometimes be replaced by aluminum atom. So that's aluminum in the octahedral. Now the aluminum has a +3 charge. Now by that substitution, you create some sort of charge right there. And then sometimes aluminum in the octahedral can be substituted by what you call base cations that are generally found within what you call hexagonal holes within the clay. So those base cations are usually in the form of 2+, aluminum ion, of course, in the form of 3+. And by replacing the 3+ charge with a 2+ charge, you create negative charges on the surface of the clay. So that is what is being pictured here. Now, those negative charges are responsible for interacting with your cations in soils, like from your fertilizer. So you might hear, of course, you practice in agriculture, you will be familiar with the term cationic exchange capacity. So it's the ability of minerals in the soil to hold those charges and then replace them at some point when they come in solution. So that is why we want to focus on clay a little bit because of that. Now, before I forget, you have right here what you call an interlayer. So between this first layer and this second layer of the 2-to-1 clay, you have an interlayer. And this layer often lends itself to what you call intercalation, which is basically material going between the layers. So small enough molecule can fit in there. And that is where water sits sometimes. So if you put a clay in the oven and you dry it at extreme temperatures and you check it with an infrared spectrometer, you will find that you will still have water molecule being displayed on the clay. Now, of course, minerals in soils do not exist in isolation or just by themselves. So they are in different proportions. And based on the proportion those minerals are in, they form these what you call textorial classes, which are represented by the textorial triangle. So the textorial triangle basically represents clays from 0 to 100% on this axis, and then silt, and then sand. Now, in order for a soil to be classified as being sandy, it has to have a minimum of 70% sand and less than 15% clay. And by that virtue, there are only 2 classes of soils that are sandy, right? For loamy soils, you have up to 7 classes, and each class is basically demarcated by these very broad lines. You have up to 7 classes, and that basically, for soils to be loamy, they have to have 40 to 50% of either sand or silt. And then the nomenclature that comes in front, whether it's sandy clay loam or silty clay loam, really depends on the percentage of the sand or silt. So whichever is the higher. If the silt is 50 or if the sand is 50, then it takes that name first. And of course, then there's clay soils. And I think there are about 3 categories of those. So the way the triangle works, if you were to say send a sample, a bulk sample to the lab for textural analysis, you'll probably get some results like this. 5% sand, 45 silt, 15% clay. And the way this works, you first identify your clay, so you're 15%, and you come across horizontally. So you're coming across horizontally to the sand line. So you're going like this. Then your silt, so 45% silt, you would identify your 45% silt and you would come down. And then of course your clays, sorry, your sand, your 40% sand, and then you will go, in this case, you will go up. So where those 3 lines intersect, that is your textural class. Now in this case, that would be your loamy soil, right? And if you notice, it's a relatively small percentage of clay that is in there. But the thing is, it takes a relatively small amount of clay to actually confer clay properties to a soil. Do we have any questions or concerns? No?
I have a question.
Yes.
Do you have any non-lab based way to have a fast method to test that percentage?
No, but you can actually feel. You can actually feel the soil, because sometimes when we're out in the field sampling, what we do is just grab a bunch of the soil. It's particularly useful if the soil is moist. So if the soils are dry out there, what we do is maybe just add a little water and just try to squeeze it between the finger and feel if we can feel any sort of grains in it. So if chances are, if you're feeling some coarseness, it's sandy. If you're feeling a little bit of smoothness, then maybe that's a sort of loamy soil. And then of course, clays, once they're wet, especially if it's Mount Marillanite, it will start becoming plastic. So you can feel that stickiness. So immediately you can say, okay, this is a clay soil, a clay soil. So that is one of the ways we identify them once we're out there. Does that answer your question?
Yes, that's good. Thanks.
Right. So the other thing about soils in terms of the way they present themselves is through structure, right? So you have all of these particles, but they're basically arranged in a certain way. So the spatial arrangement of these particles, is what determines the soil structure. Now, this you can tell in the field because you can actually see it. So if you look here, you have your granular form, you have your platy form, you have your blocky form, and you have those prism forms. And then these are actual examples of soils here that are depicting those different forms. So you can actually tell once you're in the field what the structure is, whether it's crummy or granular or platy. So you will often see this once you're in the field. So this doesn't really require laboratory analysis, but more experience. And of course, a part of this is the way soils sort of aggregate themselves. And here's actually a hierarchy of soil aggregation, where you're looking at, you have your micro aggregates and your macro aggregates. So this is just basically, each of these is a blow up, each of those is a blow up of the other. And of course, your roots, your algal hyphae, your root exudates, your microbial exudates are all important in the process of aggregation. Now here we have a micrograph and some spectra for a pure clay. This is a kaolinite clay, right? And this is the clay interacting with microbes. You can see this sort of thick coating over the clay with these microbial cells. Now that is what you call extrapolymeric substance. So exudates from the microbes. Plants will generate the same sort of things. And these are usually rich in like amino acids, low molecular weight fatty acids, and so on. And these actually help in the aggregation process. Now the micrograph here, what the spectra here is showing is that we see that the relative proportion of carbon has increased significantly from the pure clay to the aggregate. Now, what is the importance of all this, you might ask? Now, texture structure have important roles in how water is retained in the soil, how water moves in the soil. It has important implications for aeration, for root penetration, for how the soil is managed. So in the rainy season, you would not attempt to, say, till your extremely clay soils because it becomes difficult to work because of the level of plasticity, right? It has implications for heat transfer and a whole other host of sort of physiological effects on plants. Another property I want to look at briefly is soil bulk density. You might have also heard of soil particle density, but soil particle density does not really confer a significant amount of effect on soils or their functions. So we want to look primarily at bulk density. So what is bulk density? What is density? By simple definition in physics, density is the mass of something over the volume of something. All right, here we have a cube of soil. It's one of the easier representations. And remember from the first information slide, we said that soil is solid along with air and water sitting in those pore space. So to determine bulk density, it's the dry mass of the soil. That means water is taken away. So essentially what happens, you'll collect a sample in the field. You'll oven dry that sample for 24 hours at about 105 degrees, and that should remove all the water. Then that mass is divided by the total volume of the soil. Now that total volume is a combination of both air, it's the pore space without water. So it's air and solid, right? Which is what has been pictured here. And then a mathematical formula, density, this sign here means rho, it's called rho, means density, is your dry mass over your volume. Now particle density is usually twice that of your bulk density. And the reason for that is, should you ever need this information, you're looking at particle density. So that volume, which was now 1, which has now become half, because remember that 50% of soils is basically airspace filled with either water, pore space filled with either water or air. But all of that is now gone, so you're just now looking at these solids, right? Now, bulk density is quite important in that it determines, for example, your root penetration, right? It determines, you can use it as an indicator for your soil health. You can use it as an indicator, or you can actually look at bulk density and determine soil management, right? So bulk density is actually influenced by soil texture and also by management. So when you start compacting, you'll find that your bulk density will increase. Bulk density also increase with depth of soil. So your A layer or your A horizon will generally have a lighter bulk density than your deeper horizons. Also, you'll find that if you have high organic matter content, the bulk density of the soil is very low. So take, for example, samples which are organic rich. low bulk density. But then if you start going into your mineral soils, your density starts increasing, right? And your bulk is already low for your clay soil, so your thin poor soils have lower bulk, generally fluctuate with whether or not what it is, and when it's dry, the bulk density increases. Now here's based on this formula here, or we can attempt it together. So it says a cube of soil measures 10 centimeter by 10 centimeter by 10 centimeter. Now, what information can you get from that? You can get both area and both density. Sorry, volume. So volume, length times width times height. Now, if your soil is not in the form of a cube, which is probably most likely not, here's an instrument that we use to sample for bulk density. Now, this is cylindrical. Now, to determine the area of a cylinder, it's pi r square, right? So it's pi times your radius square. And to determine the volume of that cylinder, it is times the height of the cylinder. So that gives you volume. Now it says that the total wet mass is 1460 grams, including water, right? So how do you find the dry mass for that?
Dr. Spence, we have a question.
Yes.
What is hard pan? That's a question from Nigel.
Hard pan. So this is basically sort of impermeable layer that is formed with these sort of clay material. So again, it's a form of structure. It's highly compact, highly dense.
Question.
A question also
Graph. Oh, sorry.
Yeah.
Your graph, where hard pan will fall?
Sorry, I didn't hear the question.
With this graphic, the bulk density, soil texture, and soil depth relationship, where's hard pan?
So hard pan would probably be somewhere down here. So the bulk density of that would be very, very heavy. Right, because compaction, remember compaction is one of the things that affect bulk density. Right, so the more compact is the higher the bulk density. All right, so we have any questions this question? What would our dry mass?
We didn't hear what you asked us.
No takers?
We asked you for a few minutes. So what did you ask?
No. Sorry, I'm saying that we have a question here that we want to work out the bulk density for this soil. So we said that we have a soil cube, 10 centimeter by 10 centimeter by 10 centimeter, right? So we can work the volume out easily, which is 10 times 10 times 10, which is 1,000. And we said that the soil has a wet weight of 1460 grams, including 260 grams of water. So what's the dry weight? $1,200 grams, right? So 260 grams of water minus, you're gonna take that from 1460 grams and you have 1,200 grams. So the density or the bulk density of this soil would be 1,200 grams divided by 1,000, which is the volume, and you'd get 1.2 grams per centimeter cube. So that bulk density would fall about here. Now, a soil of that bulk density, you see that this is cultivated clay and silt loam. So again, bulk density can give you an indication of what soils are suitable for cultivation. I know there are some soils, for example, in Trinidad, I've seen from a presentation some time ago, that are so difficult to work. They're so plastic when wet, and they're so stiff when they're dry, that of course they can't be tilled. Now, soils like those would probably fall within this range here. So if you were to do a bulk density sampling and you realize that your samples are coming out in this range, then you have some concerns there. Any other question, Melissa, in the chat?
No other questions as yet, Dr. Spence.
Okay. Is everyone following so far, by the way? Yes, can I get an indication from someone?
Yes.
Emmanuel. Mr.
Yes.
Emmanuel. Yes, I see your hand up, sir.
Yeah, so thanks. Thank you for acknowledging me, Adrian.
Yes.
When I look at, say, for example, the island of Dominica.
Yes, sir.
Yeah, you're familiar with that island, right?
Yes, sir. Yes, sir.
Okay, so in the, what would we call the southeastern area of that island, there had been, after the severe storms which passed over the years, the last few years, you have areas which have actually villages which have been washed away. Yeah, so you have a lot of alluvial material in that area.
Right.
You would agree? How would you now determine the bulk density? I'm just trying to juxtapose how the bulk density for that type of area would be calculated, and whether it would be a true representation of the area in itself. I would imagine that what was the terminology used to categorize the soils in that particular area, that would eventually change too. And would it be something over time too that can be affected? Bearing in mind that the alluvial deposits is recent, no?
Yes.
And I imagine that over time, in as much as you would have the impact of the rain itself, which might do some form of compacting, it would eventually change over time. What is your take on that?
Yes, that's indeed correct. That's a very good question, Mr. Emmanuel. So generally, when you sample for bulk density, you want to look for reasonably undisturbed soils that haven't been cultivated or disturbed by whatever form for a year or two or so. But in this case, you could always use bulk density to monitor changes that are occurring on a spatial basis, temporal basis rather. So you could maybe do an initial sample, see what the bulk density is like there. And then as conditions change, you can continue to sample periodically and then monitor the changes in bulk density. That will give you an indication of whether or not you're having some level of compaction, or whether or not other biophysical work are at play. Microbes might start, there's some sort of activity in here, and then by aggregating the soil, this bulk density might change a little bit over time. Plants might start growing in it, and root exudates from plant could also influence change. And then, of course, if you have traffic, whether vehicular or pedestrian traffic over the area, this might also change from time to time. Even rain events can generally cause some amount of compaction, and cause changes here. So yeah,
we're having some questions.
That's a very good question. But it's yes.
Okay, Dr. Spence, are you hearing us? We're having some other questions coming in. All right,
yes,
soil amendments. Soil amendments would be applicable to which of the soils?
Right, so it depends on the amendment, because soil amendment in numerous forms, depending on what you're trying to achieve. So you could be trying to achieve an elevation in pH, for example. So you might be amending with your calcium oxide, which is your lime. Or you could be looking at something like amending with organics. Now, if you're amending with organics, then depending on the proportion of organics that you're including, then you can also change that bulk density. Because remember, the higher the organic fraction, the lower the bulk density. So sometimes when I go to collect a sample, when I pick that sample up in the core, I can actually feel that core and say, without doing any sort of analysis on it, that this soil has maybe X amount of organics in it, or a certain percentage of organic matter, just by feeling the thing. So the mass of it. So if the mass is small, and the volume remains the same, then the density is going to be smaller. So it depends on the type of amendment that you're using.
We have two other questions.
Any other questions?
Yes, could you just please again explain net negative charge of clay?
Sure. So we say clay have what you call isomorphic substitution. The major cations in clay are the silicon cations and the aluminum cations. Silicon cations has +4, the aluminum a +3 charge. So aluminum can replace silicon, and that creates a charge. Or aluminum can be replaced by what you call base cations, which are your magnesium, your calcium, and so on, your manganese. Now, if you replace, those are 2+ charges. If you replace aluminum with that, then you create that charge, that extra charge. And then those extra charges basically reside on the surface of the clay. So that is how the surface of clays become negative.
Great. We have two more on the previous slide. I believe it was about, yes, I believe it was about density slide. Is it grams per centimeter cubed or grams per meter cubed?
No, so for volume, density, for the bulk density, let me go back to that slide.
That slide, yes.
Right. So it would be grams per centimeter cube. Here you have megagrams per meter cube, but all of these are factors of each other. So whether grams or megagrams, you divide out by the relative number and you get the thing. So it's per centimeter cube. So this basically is just a bigger number, but it's the grams per centimeter cube is essentially the same thing. Different units, but saying the same thing. They're just factors of each other or multiples of each other.
We have one more question. Yes, one more for this section from Annika. Annika, go ahead.
Hi, good morning. So I'm glad you went back to this slide. I was just going to point out that you didn't calculate the water content.
No,
just
we're going to
something
do that.
Oh, okay.
No, we're going to do that. Right.
Okay.
But
no
I just want to show you that by collecting a bulk density sample, you also have the opportunity to determine water content from that. Right. So it's a very versatile approach to use. Now, I reckon probably I'm taking a little bit more time than I have to on the slides. So the next thing we want to look at is basically, water in soils. So you might be familiar with some terms: cohesion, adhesion, and of course, capillarity. Now, all of those are basically conferred by the property of the water molecule. So water molecule is one oxygen with 2 hydrogen bonded at an angle. Now, water molecules are polar molecules. And the reason they're polar is that because you have this thing that we call electronegativity. Now, the electronegativity of an atom basically determines its reactivity. Oxygen is a more reactive atom than hydrogen. It has a big electronegative. So this is about 3.2 and this is about 2.1. The water is oxygen covalently bonded to hydrogen. So that means they're sharing electrons. But electrons which are negatively charged are not equally shared. So you will find that they will be circling both the hydrogen and the oxygen, but because of the reactivity of the oxygen, they tend to pull towards the oxygen more. So even though in a covalent bond, you're not necessarily supposed to have charge, you create what you call a partial charge. Now you create a partial negative charge on the oxygen because the electrons which are negative are circling that atom more. So you create a partial negative charge, while on the hydrogen, you create a partial positive charge. And this now allows the water molecule to be able to take up nutrients, for example. So your nutrients will come in the form of what you call cations. So your calcium, which is a 2+, your magnesium, your potassium, which is a plus, and your sodium a plus. Now that negative will react with those positive, and you have that attraction, right? So what's cohesion? That's basically what is pictured here. So water molecules binding to themselves via hydrogen bonding. So this is what is depicted in hydrogen bonding. So between hydrogen and oxygen. So it's some sort of force. It's a relatively weak force that is connecting those two molecules or two atoms, right? So you have cohesion. And then now the water molecule is also able to bind to sign particles, what you call adhesion or adsorption, right? Again, by hydrogen bonding. And then, of course, we mentioned before that water can now bind to clays because clays have these negative charges, and then these positives down here, partial positives, can also stick to that. So that is what we have there. Now, what is pictured here is what you call surface tension, which basically is at the water-air interface, right? So what it looks like here is like a membrane stretched over the soil, right? And that is because it's a function of this bonding here, the hydrogen water being bonded to this, plus the cohesion. Now, because the attraction between water molecules themselves that attraction is stronger than the attraction between the water molecule and air, you get this sort of stretching effect. Now, this stretching effect results in what you call, or helps to promote what you call capillarity, which is essentially water moving upwards in the pores, which is what is shown here. So the narrower the pores, example, your clays, which are finer particles, have narrow pores, the further up the water will move, versus say your sandy soils, which have larger pores, then the water basically resides lower down, right? So bear that in mind, which is what is also shown here. So if you double what you call the internal diameter of the thing, then you half the amount of water you pick up in there. We're going to be looking at some energy concepts in water, because water content is one thing, but when you look at water content, you have to look at water content with also what is known as the water potential, right? And the water potential basically is what determines where and how water is moved or how it is retained in soils, right? So we said that the retention and movement of water in soils, uptake and translocation to plant, loss to the atmosphere, all energy related, right? So water running off some slope after a heavy shower of rain, or water running in a river, that is kinetic energy at play, energy in motion. But water sitting in soil is basically potential energy. So kinetic energy has little or no effect on water in soils. What is more important is the potential energy, water potential. That is what is responsible for water movement in soils. And this is basically driven by three forces: the matrix force, the osmotic force, not so much, because this basically controls the movement of water from soil to plants. So osmotic force basically requires a semi-permeable membrane. you know, osmosis, moving from a region of high concentration to a region of low concentration. So the water in soil is generally purer than the water in plants, because water in plants would have an exceedingly high number of ions dissolved in it, and so on, and other things. And then, of course, you have what you call the gravity potential. Now, the metric potential has to do with water attached to soil surface. So if you look here, what you're seeing is a soil particle with a significant amount of water around it. So in this state, the water potential is almost zero. So at rest, there's no energy. It's almost zero, right? So there's a lot of free movement of water here. But as the soil dries out, then the water fills around the soil that smallness, potential or psi, is given in pressure measurements, which is basically kilopascals, right? So zero, a water potential of zero is high, and a negative value, water potential is low. Right? So this is what water looks like in the pores, so sitting in pores. And as the thing dries out, it moves to the corners and becomes more difficult. Now, what this means for a plant, or absorption or take up of water by a plant, is that much more energy is now required by the plant to extract that water for its use. Right? And here we have pictured what you call a tensiometer, which is something that can be deployed in the field to basically look at your water potential. So from this, you're able to tell whether or not your soil has water that is usable to the plant. And we look at that a little further down here. Characteristic. So what it's showing is that size or proportion of different water retention. So if you look at water point 2, you have a potential of -1 for sand, for loam, -100, and for clay, you're almost well, it's probably about 1500, because this is a log scale, right? So it means then that in these soils, plants would have to exert more energy to extract this water. So even though the water content is the same, more energy is required to be exerted by the plant to take that water up. And of course, all of these things have implication for managing water, for managing soils. So especially if you're going to be applying irrigation water, which is water that comes at a cost, then you probably want to be equipped with some of this information. Again, we go back to this. So the part of the question that we left up here was to ask you to calculate the gravimetric and volumetric water content from the same core sample that was collected, right? So gravimetric water, that is basically mass of water over mass of soil, right? And this is dried soil. So to determine the mass of water in the soil, you take a sample, you weigh the sample fresh from the field, and then you oven dry that sample. And the difference in the masses basically represents the amount of water that the soil has lost. Now that mass over the dry mass of the soil would give you the gravimetric water content. You can also determine this as a volumetric water content, which is volume of water over volume of soil. With this little formula here. So you rearrange density equal mass over volume to get this. So essentially what this works out to is your gravimetric water times the density of soil over the density of water. And this density here is essentially the bulk density which you previously determined. Right? So you could also use this to determine how far up in the soil column the water actually comes. Right? The density of water, by the way, is 1. Right? So because the density of water is 1 gram per centimeter cube. So that's a standard figure you can use right there. Now what's shown here is a way of measuring water content in soil, and this is by using real-time measurements. So this is a project that I actually worked on previously. It's a climate data thing here that we worked on. But the thing about this is that you have to use this direct method in order to calibrate this method. So the direct method requires no calibration, but this method has to be calibrated by the use of this. So this real-time thing here, basically it's hooked up to a weather station and it sends the data back on soil water content to some location in real time. So we have a few of these installed around the place. Again, looking some more at, what's called a qualitative wetness of water. So you have what you call a maximum retentive capacity of a soil. So after a shower of rain, place is inundated. So the water sitting there, potential 0, maximum retentive capacity. So that's the maximum amount of water the soil can hold. After a couple of days, depending on the soil type, this water basically drains off and they are now at what you call field capacity. So remember, soil, solids, pore space with air and water. So in this case, at maximum retentive capacity, all the air has moved out. And all the pore spaces are enough water, because remember that air is also important for your metabolic activities in soil, right? So this is where you want to be essentially. Now that's about, this can go range between -10 and -30 kilopascals, depending on the soil type. So as you progress further, whether you have a nude soil, sorry, my bad, I didn't turn my phone off. Whether you had a nude soil or you have soil that is vegetative, you will continue to lose water. So from the nude soil, you lose water through evaporation. From the vegetative soil, you're going to lose water through transpiration. And there's some evaporation as well. So you get down to a point now you call the wilting coefficient or wilting percentage. Now at this point, it's about -1500 kilopascals, where the water around the soil particles is now in an extremely thin film and requires a lot more energy. Now, beyond this point, plants are not able to extract water because they cannot produce that much energy, right? So plants are not able. And then what you have, you start having wilting, or the plants basically have to close their stomatal pores in order to reduce water loss. And then the plant starves by not being able to take up carbon dioxide. And then of course we have what you call a hygroscopic coefficient. Now here, it's just basically water that is attached to clay and essentially irremovable. So even under oven drying, it's extremely difficult to take this water off. And here we're just looking at some figures, basically showing clay, of course, being able to hold a lot more water than other soils, but a lot of that water is unavailable because of this very strong force that is holding that. So once you're down to hygroscopic, you're at -3000 or thereabout kilopascals, which requires extreme energy to overcome this attachment. All right, so again, showing field capacity. This is something you can improve. There was a question earlier about amendments. This is something you can improve by adding organic matter. So here, plant available water is down here, but by the time you've added some OM, you've pushed that up a little bit. So looking at drainage, I won't have to run through this part quickly because I'm kind of on time. Any questions here, Melissa?
No questions as yet.
Okay.
Except we're having some issues sometime with the screen freezing. So perhaps if you turn the video off for a little while, it may help.
Right. So yeah, as I told you, my internet here
Yes.
can be a little sketchy.
We do have a question from Brenda, Dr. Spence.
Yes, please.
What are some of the factors that can affect the soil structure?
Right. Good question. So tillage affects soil structure. Fertilizer application, type of plants. If you have trees, for example, and those roots with a lot of force can actually break soil structure up, right? But the main management practice that you can use to change soil structure is tillage, along with fertilizer application. So here now, kind of, anybody else?
No, not right now.
Am I being clear to everyone? Please feel free to interrupt because I know some of this stuff might be a little bit heavy.
Oh, we have a question coming in from Nigel. How does tillage affect? Nigel? Structure. How does tillage affect structure? The follow-on question.
Right, so say for example, you have a platy structure. And you start tilling that, then you start breaking those plates into smaller bits. Now by breaking those plates into smaller bits, you allow them to be now influenced by soil factors that could actually change them to be, say, crummy. So when you start that sort of aggregation of those smaller particles, then this might become, form part of the crummy structure. Right, but tillage just breaks the thing up into smaller fragments, which now allows it to be influenced by other things.
Okay, we have one more question here.
Yes.
So Finola says that she has heard of a no-till approach to soil health. Can you tell us how that works?
So no-till is essentially you're planting, and essentially the only area that you will be, say, managing or disturbing is the area where that plant is going to be sitting. So rather than an extensive approach, right? So you just prepare like a hole to put a plant in, but the rest of the soil remains undisturbed. And this is particularly useful when you want to use soil as a way of conserving carbon. Because once you till the soil and you break those aggregates up, again, start breaking up your structure, then these things become exposed and now are available for microbial activity. So once microbes starts accessing that previously inaccessible carbon, then it becomes mineralized. And once it becomes mineralized, there's only one place for that to go. And that CO2 is going to be moving from the soil, which is an area of high concentration in CO2, to the atmosphere, which is actually of low concentration in CO2. Anybody else?
No other questions right now.
Okay. So we're looking at fate of water. What happens after precipitation? The water can either be stored in soil, it can either run off to some place, and you have evaporation, and so on. So look at this equation. Precipitation is equal to evapotranspiration plus soil storage plus discharge. Right? And if you rearrange this, you get discharge, transpiration minus soil storage. And it says that the only way to decrease, I would really do better with the chartboard. But the only way to, so this shows that discharge can only be increased if these two components here are decreased. You don't necessarily want to decrease soil storage, not for agricultural purposes, right? You would want to, however, influence evapotranspiration if you can. But the idea is to minimize discharge. Now, this becomes particularly useful, especially if you're using irrigation water. Again, this is water at a cost. So it might be useful to consider ways in which you can encourage soil storage. And then now this is one of the ways. So this thing here that is showing a field with basically these, I would like to call them micro ponds that you allow the water to sit in there. So you give the water more time that allows it to percolate the soil. So rather than this water running off right away, it sits there and percolates the soil. Attributes. The soil physical properties including from penetrating. So it's almost impermeable, right? So these sort of things help to determine water movement. So if you look at this arrow, it shows that a large amount of this water is now actually moving laterally than moving vertically because of this structure here, right? So that's another way in which soil structure influence water retention and water movement. And of course, this will also have implication for plant root penetration and so on, right? And then you can look at these things here, which basically show how structure impact the amount of water that is absorbed. Topography is another important thing, and the presence of vegetation, right? So you look at the size of the arrow basically indicates the amount of water that is going where. So here you have a little bit of water coming in because the structure is probably a well compact structure, but a lot of water going over surface, right? And in here you have a lot more water going in. So this is a more friable, a more aggregated structure that allows penetration and less going over there. But once you've added vegetation to this topography, it sort of changes the dynamics of things a little bit. Now we're looking at enhancing drainage. So too much water can have negative implications for a farmer because air is equally as important as water, or almost as important as water in the ability of plants to assimilate things and to thrive, right? So oxygen is required for metabolic activity. So for microbes to whatever, for the roots to breathe, air is required for that. So in a case where you have the water table that is very high, then drainage is actually important to remove that water. So you'd cut drainage below the water table and try to slope it away from the farm. But you have also what you call a perch water table, which again is a function of impermeable structures, right? That basically sit here. But all of this can be improved through drainage. Now this is showing basically some of the physiological effects, or should I say anatomical effects on plants. So where the water table is high, then root development in the early stage is basically retarded. Now this becomes a problem when the water level recedes, because having been stunted, these roots are now not able to reach deeper down to extract that available water. So an early remedy to this is to actually put in some sort of drainage, subsurface most likely, to take that water away. And here are some examples of drainage. Subsurface, it's an open ditch, and here we're using these tiles, which basically holes in pipe. So recommended generally to actually turn the holes down so as to avoid stuff like this. Because if holes are up, then what you have is all of this being filled with soils. And here we have some advantages and disadvantages of artificial drainage. I'll not necessarily read this because you guys will have the presentation. And some of these things have been mentioned already. So more air, the better it is for plants because they're able to breathe. There's more microbial activity, and microbial activity is basically responsible for breaking down organic matter to make it available to plant. You have your gaseous exchange and so on. Now, a lot of the disadvantages here are sometimes related to your wetlands. So if you drain a wetland, then you basically disrupt habitats, you basically disrupt a number of ecosystem services and so on, right? And looking a little bit at irrigation. So from time to time, irrigation water might become necessary, especially on a seasonal basis. And of course, we know that agriculture is the highest user of fresh water globally. So it's about, I say, 80% globally. Could be higher in places, right? And these are some examples of some irrigation system we have here. So open ditch. We might all be familiar with these. There is the lined and there's the unlined. Now, the disadvantage of this is that water loss to adjoining soils. So lining basically prevents that loss, but you still suffer from evaporative loss. So it's a highly inefficient system, but relatively cheap. And here the water has been siphoned off to the fields. One of the problems with this form of irrigation, though, is the uneven distribution of water, which is actually pictured here. And again, this is influenced by your soil type. So you have at some point where your water will enter and that will move down a gradient, right? But if you have like a very loamy soil or soil with a fairly loose structure, then a lot of that water comes off close to the origin very quickly. And you have this sort of scenario developing versus getting down to the end of the field where it more or less becomes a little dry. So you can notice the difference in plants here. And if you look at this in terms of productivity, then you will realize that you have greater productivity at one end and plants not doing so well at the other end. The reverse might be true if the soil were clay. So because it's clay, then the percolation of water takes a little bit more time. So you will have this now sitting at the other end. Right, so knowing your soil type is an important attribute when you're actually applying irrigation water. And of course, the rate at which your plants and so on might take up water. And there's a very useful soil moisture probe. It's one of those automated ones as well. The brand is called Semtech, I think, which is what you call a dig and drop. So you punch a hole and you drop the thing down there, and it gives you the water penetration in the soil at certain depths. Even when you have rainfall and so on, you can see where the spikes are and so on. Very, very useful. That requires another webinar by itself. And of course, sprinkler irrigation, which we're all familiar with, widely used, but then again suffers some negative fate in terms of water losses. So water is deposited on leaves of plants, which is basically left to the mercy of evaporation. You also have evaporative losses when you create the sort of mist, so wind-blown evaporation becomes an issue right there. The thing about this though is that it creates a really, really cool condition for the plants, which the plants sort of favor. But the best of them, or the most efficient of them, is your micro irrigation system or your drip system, which is basically a targeted approach. So you can control the amount and the timing of the water, and also, a sort of precise application. One problem with drip irrigation, though, is that because the amount of water that is added to the root of the plant is so small, oftentimes the soil is not saturated, for want of a better expression. So if that happens, and you should incur a massive dry season with little or no water to add by irrigation, then your plants would have suffered because there is little or no water in soil to sustain them. And lastly, we want to look at the thermal effects of some thermal properties of soil. Heat in soils often overlooked in the same way, the function of soils are overlooked. But heating soils is pretty critical. Again, it's responsible for a number of activities, some of which are outlined here. So your germination, for example, certain plants basically will only grow within a narrow temperature range. So managing the thermal exchange in your soils is sometimes critical. So if you look here at these things in terms of soil organic matter loss, so both carbon and nitrogen together, soil organic matter, you'll realize that you have higher losses when the soil is heated. And that is a function of microbes being able to operate at higher temperatures. So your microbial enzymes that are breaking down your organics require a particular, what you call temperature maximum. If you remember some biochemistry, you talk about your Michaelis-Menten curve, which basically looks at heat requirement for some of these things, right? So heat is something that you want to manage in your soils. Now, this has implications, of course, for emissions to the atmosphere. So where does heat in the soils come from? Of course, from solar radiation. So some of this small proportion basically heats the soil. A lot of it is actually reflected back to the atmosphere from the soil surface. That is called albedo, which basically depends on the roughness and the color of the surface. Right? So a lot of it goes back out. Right? Now, how does this heat move in soil? And of course, the amount that, before I go on, the amount that reaches the surface is a function of, say, your cloudiness or the amount of dust particles that are present. So on a day when you have the sub-Saharan dust coming over, you might realize that there's limited amount of sun reaching the Earth's surface. Right, so how does heat travel in soils? So basically through pores. So if you look at this, pores are, the particles are loose, so you have wide pore spaces, versus here, where the soil is a little bit more compacted and there is water present. So the size of the arrow basically indicates the amount of heat that is being transferred from surface to a deeper level. Now, why is this so? This is so because water is actually a better conductor of heat than air. So all of these, just air within these spaces. And here, even though this is probably the same amount of water, it's still transferring a larger portion of heat because now the particles are compacted. So there's heat transfer, energy transfer from particle to particle. Any questions? All right, I believe
None
this
yet.
is, say again?
None yet.
All right, I believe this might be my last slide. So how do we actually regulate soil temperature? Well, one of the ways to do that is mulching. So organic mulch, which basically works at temperature extremes. So if the soil is hot, it keeps it cool. And where the soil is cool, it can basically provide some warmth. And remember that soil temperature is important for a number of functions, both for the plant itself and other support systems, such as your microbial activity and so on. Right, so that's organic mulch. And then we have here pictured is a plastic mulch. So unlike your organic mulch, what a plastic mulch actually does is to keep the soil warm. So this is something that is often used in like temperate climate to sort of extend the growing season and so on, right? And of course, the clear mulch is actually more effective heating the thing than the black mulch, the black plastic mulch. And then finally, I want to look at this diagram here, which basically speaks about the implications of wildfire for a change in soil structure. And this is another way you can change your soil structure, through burning. So at extremely high temperatures, some of those volatile organic carbons basically recondense and they form this sort of waxy repellent that is deposited lower in the soil. So again, this is going to affect your water movement and retention, your water penetration or percolation, your root penetration, and of course it will affect your microbial activities and so on, right? So that is essentially what that is showing. One other important thing about temperature in soils is that sometimes at regular soils operating at regular temperature basically creates enough heat to remove some of these volatile organic carbons without causing this issue of condensation, right? So it's this extreme heat that is basically responsible for that sort of matter. And I believe that is the end of my presentation. So I know I ran a little over time, accommodated a good few questions. So I apologize for that, but I hope that the material wasn't too heavy and that it was quite palatable and will be assimilated well. Thank you. So I will entertain some more questions, Melissa, if there's time for that.
Sure, we can take a few questions, Dr. Spence. We have a question from George. George, please.
Okay, thank you for acknowledging me, Melissa, first. I think there are other questions in the chat, but yeah. Wonderful presentation, Mr. Spence. Very technical and scientific at that. Certainly, it reminds me of being back in university, So anyway, that's good, and I like it. So as interesting as yesterday. Towards the latter part of your presentation, you spoke about the soil covers and the mulching. So soil solarization, when they put these plastics to control weeds and to actually destroy, pretty much, it would, some of the microorganisms and so. How does that affect the structure in its sense? I know for certain that the temperature is increased and microorganisms die, and the porosity might be increased, but does it affect the texture pretty much, or how would you relate to that then?
So texture doesn't necessarily change regardless of whatever management practice is employed, but structure, you might have it's easier to have an influence on structure than texture. In terms of how this particular approach changes structure, no, I couldn't say. But from my limited knowledge, I cannot really think of a way now that says using mulch basically changes, this type of mulch basically changes the structure. I know for like your organic mulch, your green mulch, because that over time will degrade and basically form part of the organic component of the soil, then of course you can modify the structure somewhat, especially for that top layer of the soil. So it should become a little bit more granulated.
Yeah, and then a little follow-up to that, Mr. Spence. Yeah, man, you answered the question. I know it's a kind of difficult one, even for me to try to internalize and so. But the other aspect is the the biodegradable mulch.
Right.
According to what it said, biodegradable, and even those which take like forever to actually disintegrate.
Yes.
It increases the porosity to a certain extent, or what do you think? Because I say this because of the nature of the material itself. We spoke about the adhesion and the cohesion and how it would adhere to the particles and so, but does it make it more friable? I think that's the word, or I don't know.
Right. So being granulated, it's more friable. And of course, if it's more granulated, then the porosity will also increase. So the ease of root penetration, the ease of water percolation, and so on, all of those things will improve. The depth at which that occurs, though, I wouldn't know. As I said, most of this would be superficial.
Yeah, thanks, Mr. Spence.
Sure.
A question from Kashar. Would the black plastic mulch be recommended here, or would it be too hot for plants?
Well, actually, the clear plastic generates more heat So yes, I think it would be applicable here.
How does soil tensiometers are used in precision agriculture for automated irrigation?
Right, so you'd basically punch a hole. So the tensiometer is actually filled with water, right? And you'd punch a hole in the soil, and then it's planted, and the soil is used to secure it. So essentially you want it to be a very close fit. Now, depending on how dry the soil is, the level of that water will actually decrease. Now, as the water decreases, then the meter moves, right? And that will tell you the sort of pressure potential that you have there. Now, remember, sorry, you can indicate, you can use those pressure measurements to indicate the relative amount of water you have there, or whether or not you have usable water in the plants. So if you're down, so at field capacity, it's 10 to 30 kilopascals. At hygroscopic coefficient, it's about minus 1500. So if you're somewhere between there, then that is a good indication of whether or not you need to add irrigation water depending on your soil type. So remember, if you're clay, you will have soils down there, water down there in the soils, but that water is not necessarily available because it's hygroscopically attached to the soil particles, and it will require extreme amount of force from the plant to extract that water. So there's little or no free movement, right? So that is how you essentially use the tensiometer to indicate whether or not you want to irrigate and so on. With the automated soil moisture systems, this would basically send information back to you at wherever, so you can determine from a remote location whether or not you need to irrigate, versus say the tensiometer, which you will have to go in the field and check. The beauty about the tensiometer is that it can be used by just about anyone. It's just a matter of understanding the pressure measurements.
Okay, thank you. We have a final question. How does the use of lime affect the structure and biological life in the soil in relation to the physical properties of the soil?
Right. So liming, I don't know if liming affects, and I stand corrected here, I don't know if liming affects structure, but I know liming impacts a number of chemical properties. So your pH, for example, because that's the primary reason why liming is generally applied to improve soil pH, because most of our soils, cultivated soils, are actually at acidic pH, and depending on your crops, you might need a particular range. So I know for certain it affects the chemical makeup, but I couldn't tell you how it affects or if it does impact the sort of physical properties of the soil. The only thing I could say about in sort of a powdered form, which would have a very large surface area, right? So if it has the capacity to, say, absorb water, then that might impact your water movement and retention, pretty much in the same way that clays would. Not necessarily at the same level, but basically the same principle, because one of the ways that clays impact water retention in soil is because of its large surface area. But then again, remember that clay also has the charged surface and then layers through which water can be intercalated, right? So in terms of surface area, it might impact water retention. I think that's the best I can answer that question.
Okay. Thank you, Dr. Spence. Thank you, colleagues. We're at the end of Module 5. And thank you for your questions. Thank you, Dr. Spence, for your very rich presentation. I hope we're able to take many points from it. We are upon a break. It's 10:35 here by my clock. We will take a 5-minute break. and we will be back at 10:40 a.m., a 5-minute break. If you do have any other questions, please type them in the chat. Thank you.
Melissa, I just wanted to say that thank you very much, Adrian. And I think you all have to think about part 2 of this training, okay? Because people are telling me this is too much information, too short, gray information. So think about part 2.
All right. I mean, as I indicated before, people can always reach out to me with whatever questions or whatever clarifications that might be needed. I'm always open. And it doesn't necessarily have to be about, this particular thing, but kind of roughly anything in soils.
Myra, are you still there?
Hello, this is Harris.
No, I was just wondering if the answer was good for Omera. She didn't respond.
Oh, yes. I mean, I could, as I said, yesterday I had mentioned that, I am open to people reaching out after, and I'm sure my colleagues would be. And it doesn't necessarily have to be on these specific issues relating to soils, but soils on a whole, that's my area of expertise. So I'm always open.
All right. And I also think this is a good time to interject that a manual will be produced that
Right.
you will get as a participant to further digest some of this, because as in school, you don't digest at the lectures. You have to go home and study. So we do expect that you will study the information once the manual is distributed to you.
Right. I did indicate that yesterday that will be a major part of the training as well. But I'm always open.
Yes, hello, good morning, Adrian. I think, yes, what our colleagues are mentioning is very important. And specifically for us here in Belize,
Yes.
we work with the sugar industry, and there are two important things that impact our soils.
Yes.
The traffic, whenever they're harvesting and doing management practices of the fields, and also the burning. So I think it will be
Yes.
very good to continue having this type of topics to be discussed.
Yes,
Because
absolutely.
we learn more now. I think a lot of concepts that you discussed, but again, the time is very limited, and we would like more information about that. So I think we can, if another session can be programmed,
we can,
where we can.
If for your particular needs, we can set up another Zoom at another time, and we can talk about these issues a little bit more extensively. And
Okay,
in
thank
a
you.
way, yes, in a way that I mean, these sort of one-on-one sessions are usually a little bit better, or let's say intimate sessions, because sometimes there are a couple of people as well. But presenting it to you in a more intimate setting might actually help you to digest some of the material, or at least hearing it a second time probably will. But definitely, as I say, you can always reach out to me via email. We can set up a Zoom, and we can just have discussions on the thing. Because one of the things I have realized, and I do this from time to time, students, people in agriculture here, and so on. From time to time, I'm actually engaged in a lot of discussions with people on soils. Because one of the things I realize is that, throughout the Caribbean, there is not a lot of work being done in soils. I find, for example, recently, we were actually working on some digital soil carbon map for Latin America and the Caribbean. And we wanted to get some organic carbon data. And when I went to the land management division here, the most recent information they had was some extensive soil surveys that were done like back in the 1960s. So of course, we had to basically pull on what we had although we weren't necessarily focusing on organic matter in soils, to do that. So research in soils in the Caribbean on a whole is limited. And from time to time, I have to be reaching out. Well, people are reaching out to me from all across the Caribbean just for discussions on soil. So of course, that's not a problem.
All right, and we're just about ready to begin. So our next module. Dr. Allen.
Oh, okay, I was muted. So just testing now. Can you hear me?
Loud and clear.
Testing. Okay, great. Okay, let me share my screen. Okay, are you able to see where it says Module 6, Meteorological Information?
Yes, but just add the presentation view, make it a bit larger.
Yeah, yeah. Okay. Everyone can see it?
Yes.
Great, okay. So thank you. I learned more in 1 hour about soil science than I have in my entire life. So I'm still processing all that information. So we're gonna switch gears and kind of look more now in the air and not on the ground, talking about meteorological information. So the outline for this module will consist of looking at deterministic versus probabilistic forecasts. Between those two mean statistical versus dynamical forecasts, introduce you to regional outlooks and national outlooks. And the reason I'm stressing this outline is that I'm describing the type of information that's available and not necessarily what you need to produce. So all this stuff that we're going to talk about in the next 30 minutes or so can be found at your National Meteorological Service or the regional service like the Caribbean Institute for Meteorology and Hydrology. So the objectives, I'm going to stress interpretation. The interpretation of a forecast is vital. This, to me, in my experience, this is probably a difficult thing for people to get right with climate services, is interpreting the forecast. Okay. And second objective, where they can access this information, where it's available, and of course it's free of charge. Okay. So let's move on. Oh, come on. Okay. So let's take a look at this forecast example. It's just a weather forecast. I'm sure all of us have seen. At the top, you have an hourly forecast. The temperature and rainfall might change every hour. And the bottom is the daily forecast, changes every day. But if you look, let's just pay attention to that there's a actual forecast for temperature in degrees, 27, 26. But then when we look for and rainfall, it's in a probability. So why don't we forecast rainfall, or why doesn't this forecast choose to forecast rainfall percent and not an amount like temperature? Okay, well, one forecast is, yes.
I'm sorry to interrupt. We might be having some internet challenges. So if you could get the video off for a while, it would perhaps help.
Oh, okay, let's see if that helps.
Thank you.
Hold on. Sure, let's see here. Okay, is this better?
We'll see. Thanks.
Okay, we'll see. If I need to make a change, if I move from one room to the other, sometimes you really need to change. I might need 2 minutes to switch locations. Okay, so let's continue. Thank you. Okay. Forecast is more confident than the other. Would anyone like to take a guess in terms of what is usually more predictable course of a day? I'm going to send it in the chat box.
Okay, we lost the question. So if you could just repeat the question, I would give you 2 minutes to switch to the other room. And maybe that would
Okay.
give us some time to answer the question. Could you just repeat the question?
Yes, the question is which one is more predictable, temperature or rainfall?
Thank you. And we'll just
Okay.
give you 2 minutes. So
Yeah, let me switch rooms. Hold on one second.
and the question was, which one is more predictable, temperature or rainfall? Okay, so far we have more responses for temperature being more predictable than rainfall. Well, as Kay says, rain has no law. We'll see.
Are you able to hear me?
Yes, we're hearing.
Hearing
Okay,
it.
good.
All right, no longer hearing Dr. Allen.
Okay, hold on one second. Hold on. Now, can you hear me?
Yes.
Okay, hopefully this is better. I apologize for the delay. So let me, okay. So now we're back to the forecast example. So are we good?
Yes, we have more persons saying
Okay.
temperature is the answer.
Okay, exactly good. Okay, so probabilities are well suited to communicate uncertainty. So because rainfall is more of an uncertain parameter to predict, it's often, and we will see this throughout many seasonal forecast examples. Okay, so you will see values like temperature, degrees, and that's going to be the difference between deterministic and a probabilistic forecast. So let's just chat for a second about a deterministic forecast. So deterministic forecast, as we just saw, is one that gives a unique value like 27 degrees or 35 millimeters of rainfall of a future value. Okay, so in order to calculate a deterministic forecast, you have an initial state of the atmosphere and predicted to give a unique answer. Okay, now the state of the atmosphere is often described by spatial and other variables. And you can extrapolate these tendencies of these variables in time to predict the value. So basically, a deterministic forecast will forecast an exact amount. So let's take a look at this example at the bottom. Here we're looking at a seasonal forecast. Here you can see squared off in red, SON 2021. That means September, October, November for 2021. And on the left, precipitation anomaly in the blue. And here in the large red rectangle box, you can see the scale of the forecast. And because these are values up to greater than 200 millimeters, these are deterministic values, an exact answer. So let's take a look in our region. In our region, the Caribbean, we will expect during the September, October, November season, about 100 to 50 millimeters less rainfall than normal. Does everyone see how I'm getting this answer? I'm basically looking at the color scale in our region, relating it to the map, the value of the color scale. It's very straightforward, very direct. I'm sure people have a lot of experience doing this. So this isn't necessarily the complicated part. Complicated part, I should say, not as straightforward, is a probabilistic forecast. So before we just looked at the deterministic forecast, we saw 50 millimeters of rainfall less than normal within that season. Now we're going to look at a percentage-based forecast. So in contrast to deterministic forecast, a probabilistic forecast assigns a probability to each of a number of different outcomes. Okay, so let's look at our different outcomes. Variable, same season, September, October, November. Now we're looking at the probabilistic forecast. And notice our scale here is now in percent. And okay, so if we want to interpret this probabilistic forecast, what we would do is, and here you can see, okay, there's some oranges, some yellows there. That looks to be about 40 to 50%. Okay, so let me tell you first, this is how you do not want to do this. You do not want to say it'll be 40 or 50% higher. Okay, so if your average rainfall was 100 millimeters and you looked at the scale, you said, oh, it's going to be 50% more, so I'm going to expect 150 millimeters. That is not. Instead, you look at the color, and here it's representing the below normal category. You would say it's about a 40 to 50% fall across most of the region will be less than normal during the September, October, November season. Does everyone see the difference between those two?
Okay, Dr. Allen, could you just repeat what we should not do and what we should do?
Yes, okay. What you should not do is say there's going to be 40 to 50% more rainfall. That is incorrect. Because this is a probability, this is saying there is a 40 to 50% probability be less than normal. Okay, so let's break this down to a tangible example. let's rainfall for your September, October, November season is 100 millimeters. This is saying that if you have a 50% probability it's less than normal, 20 millimeters. It could be 10 millimeters. We don't care about how many millimeters less than normal. What we do care about is the probability of just being less than normal. Okay, so I emphasize this because this is a major interpreting these seasonal forecasts. And it's important because your National Weather Service and your regional meteorological seasonal forecasts that are based on probabilities, okay? And as an agro-meteorologist or someone who's interested in agroclimate, agriculture, crop, it's important that you're able to interpret it correctly, okay? So again, let me just repeat, 40 rainfall across most of the region will be less than normal. Now let's look over here and say Indonesia and New Guinea in this area here. Okay, Singapore. You can see here now these colors are dark green. Could anyone offer a suggestion on how you would interpret Asia? So someone please chime in or type in the chat box.
Yes, Dr. Allen, could you please repeat? We lost you. What
The
was the example
blue,
for Indonesia?
could you repeat that, Melissa?
You posed a question. Could you just repeat it, please, using the example?
Oh, okay. The example across Indonesia. I'm asking, could somebody give an interpretation of the seasonal forecast around Indonesia, where it's dark greens? Good, excellent. Excellent. So a lot of people writing in, and the key is higher than normal, higher than normal. Exactly. 70% more than normal. It's 70% probability of being more than normal. Okay, cool. This is great. That's important. So just to emphasize the key aspects, this is a seasonal forecast, and often your weather service will provide seasonal forecasts. The seasonal forecast does not imply that one particular month will have references the entire September, October, November season. So this is important. It will not tell you what the October will be, nor will it tell you what your probability for November will be. It simply tells you what the probability for the entire season will be, your seasonal totals. Ask me from a seasonal forecast, they've said, hey, my aunt is getting married in Guyana in late September. There during her wedding. And you absolutely cannot answer that type of information with a seasonal forecast. All right. Yeah, so that pertains to the third bullet point. You cannot use this information to plan for a specific subseasonal event. Okay. All right. Let's see a chat. Okay, question. How often is the forecast produced? Good question. So every month, a seasonal forecast is produced. So today, the Caribbean Institute for Meteorology and Hydrology will issue the seasonal forecast for September, October, November. First, we will issue the forecast. for November, October, November, December. And then November, it'll be November, December, January. So every month you have a 3-month seasonal forecast. Okay. So now what I want to do is just show you sea surface. Same thing, same parameter, sea surface temperature in both maps, both generated from the same model. On the left, we have on the right, we have a probabilistic forecast. You're welcome. Okay, so if you look at these maps, you could almost patterns. Here, there's a lot of blue in the equatorial Pacific on one. There's a lot of blue in the equatorial Pacific in the other, but just different interpretations. So on the left, you would say for the September, October, November season in 2021, the expected sea surface temperature anomalies will be about 1 degree less than normal. If you wanted to issue that information in a probabilistic forecast, you would say for the equatorial Pacific, about that area, there is about a 70 that the sea surface temperature there will be less than normal. So I've got one more question. If there's a 80% probability less than normal, what happened to the other 20%? Because everything adds up to 100%.
Okay, and you'll have to repeat for us, please.
So if there's an 80% probability of it being less than, okay. If there is an 80% probability of the sea surface temperature being less than normal, about the other 20%? Okay. Great, yeah. So there's a 20 normal or below normal. Okay. So here's the main difference between a deterministic and a probabilistic forecast. In essence, you could say in a probabilistic forecast, you are never wrong. Because if your sea surface temperature there is actually warmer than normal, chance that would happen, and it did happen. The probabilities were low, but it did happen. So the forecast is correct. On the other hand, on a deterministic forecast, if your forecast is for -1 degree Celsius cooler and it becomes 3 degrees warmer, that forecast is wrong. Incorrect. So you can see with the probabilistic forecast, you have a lot of room for interpretation. Now it's your job to determine how you would like to use the probabilities. At what threshold is the probability high? So for example, if there's equal chances for it to be above, below, or normal, say 33% for above normal, 33% for below normal, and 33% for normal, that forecast has almost no skill. It doesn't tell you anything because each category is just as likely to happen as the other. Probability is 90% for being above normal, then that's a very high probability. And if I'm making decisions, I'm probably going to make decisions that tell me that I can expect. Okay. So there are some interpretations involved here. So now let me just give you a few examples of some probabilistic. United Kingdom Meteorological Agency or Meteorological Service, and you'll see three columns of maps. On the left column, and I should back up and say these are all all forecasts, all probabilistic forecasts for air temperature, surface air temperature. First column, you have what's called terciles or divisions of 3, above normal, normal, and below normal. In the middle, you have probability of being above normal or below normal. And on the far right, you just have a probability of being above the median. So what's the probability of being? So there are some different styles of probabilistic forecast, but the most common you will see is what's called the tercile, or the 3 different categories. Okay, there are questions here. I see a chat. Okay, here's a question. What are the units for the deterministic models? Good question. The units for the deterministic model are based on whatever is being forecasted. So for example, if it's rainfall, the units would be millimeters of rainfall, degrees Celsius, or so forth. So if we go back to this example, if I can go back to it, I'm only gonna, I'm not able to go back in this. Okay. For the sea surface temperature, because sea surface temperature is measured in degrees Celsius, the unit was 1 degree Celsius below normal. Or percentages. Great. Okay, moving on. Okay, so here are just some other examples of probabilistic forecasts for sea surface temperatures for the September, October, November season from 3 different sources. Oh, 20% left, okay. From 3 different sources. Here you models. On the top right, it's from the Japanese Meteorological Agency. On the bottom right is a collection from European, Canadian, American sources. But these are all probabilistic forecasts, and you can see they all kind of say the same thing. So there's a high probability for below for all regions, for all services. And if you look in our region, it's mostly red in the Caribbean, and mostly, you know, oranges and yellows in this one for the Caribbean, and that's a higher probability for above normal. So what we do when we make forecasts, we like to look at many different forecast sources. Different places agree on their output, and if they all agree, we have confidence that this is a pretty consistent forecast. Now, if the Japanese Meteorological Agency in the equatorial Pacific and everywhere else had cold, we have to scratch our heads and try and understand which one might be better, what's driving the differences. But here, they all agree, which is often the case. Okay, now here we're going to look at an example of an institute called the International Research Institute for Climate and Society. They use both the deterministic and a probabilistic forecast. In fact, they take elements from the deterministic forecast and use it for their probabilistic forecast. Let me give you an example. Here on the y-axis are sea surface temperature anomaly, so degrees Celsius. And this is basically showing a time series of sea surface temperature anomalies based on October, September, October, November, October, November, December, all the way to April, May, and June of 2021. And each one of these lines represents a different climate model. The temperature is going in the equatorial Pacific is going to be cooler than normal, which is consistent with the La Nina. And in fact, the average, or these dark lines, say it'll below normal. So it's deterministic, it's given a value. So most of the models all agree that we will be in some sort of La Nina phase for the next few seasons. Now take that information, look to the right. Now we're looking at a probabilistic forecast of the probability of being a La Nina or an condition. So let's look at September, October, November, and the blue bar is the highest at 60%. So there's a 60% probability for September, October, November season. And look at the red. It's about 1 or 2%. So there's about less than 5, about 35% probability of being in some a neutral condition, not warm or cold. So anyway, you can have one institute that can use both deterministic and probabilistic forecasts. So now let's move from deterministic and probabilistic into statistical and dynamical. Explores the relationship between two variables, a predictor and a predicand, and it produces a forecast over time. Now, for statistical forecasts, a long-term history of observations. Why? Because if you're going to make a forecast on how rainfall is and sea surface temperature, you need to have a long time series, many, many years, to show how rainfall varies with sea surface temperature. We'll look at that in a minute. Dynamical forecasts, on the other hand, rather than taking a time series of historical observations and making a relationship, it solves equations. These equations of motion describe how the atmosphere will interact and move and change in time. Motions with temperature and so forth. So these are your dynamical. So they're very intensive, often require intensive computational resources. Back to this deterministic sea surface temperature forecast we just looked at. All these little lines here, they represent models. Some are statistical models. Okay, so they can be combined together to look at how far apart they agree. So just remember, dynamical, complex system of equations requires computational resource, high-end computational resources. Statistical requires a long-term observational time series for at least two different variables. We tend to deal more with statistical forecasts with our National Weather Service and our Regional Weather Service, Caribbean Institute of Meteorology and Hydrology, because many other forecasts that we use. So we take advantage at the Caribbean Institute of Meteorology and Hydrology and your National Weather Service of observations from or Belize or whatever your country is. Okay, so in this case, we use one variable, say for example, ocean temperature, to predict another variable, say for example, rainfall. Now let's look at this map on the left. And the red rectangle here, this is the area of sea surface temperatures that goes into producing a statistic. Okay, now the map in the middle says, okay, show me all the rainfall observations in this area here and tell me how time relative to changes in sea surface temperature. Now you'd want at least a 30-year time series of monthly records to do this properly. Statistical forecast this way, you have 30 years of monthly observations for average sea surface temperature in this area, and 30 years of monthly observations for every weather station within this location. Okay. So then you can build this forecast based on statistical relationships to produce driven by your sea surface temperature. Now, I emphasize this because that is what's often done within the Caribbean region. So if you look at a statistical forecast and it's produced by your National Weather Service or the CNMH, it was driven by sea surface temperature variabilities, okay? And sea surface temperature is used to inform. Now, here on the far right is just an example of your observations at one location in green over time. Your years are here on the x-axis. And the forecast in red. And you can see how well the forecasts compare to the actual observations from the past. And in some places, it's very. It is 1987 in this location. The forecast and the observation, the statistical model were very close. But here, say in 1997, wow, very high, but the observation wasn't very low. But if you pretend that this blue area is above normal, the green area is normal, and the red, then both of them, the observations and the forecast will be above normal. So if you have a probabilistic forecast, then in this case, the forecast. All right. So let's just take a quick look at some of the statistically driven forecast products offered by the CIMH. And I want to bring this up because these are all readily available. If you do not, actually, let me ask you a question. Who uses seasonal forecasts from either the National Weather Service or the CIMH? Does anybody climate forecasts for temperature, for rainfall, for anything else? Can I get a show of hands or shout? Are people aware of it? Are they unaware of it? Objectives is to inform you of the availability of these products for you to use as you plan any sort of agricultural activity. Anybody use these? Familiar with them? Are people hearing about them for the first time? Anyone want to chime in on the chat? Oh, good. So some people, yes, actually, yeah, I know CARDI is definitely aware of it. Okay, excellent. Yeah. Okay, so some are, and then I want you to be aware that these can be retrieved from the CIMH and also the your National Weather Service. So here we have just a rainfall September, October for 2021, and then November, December, January, this the following season for this previous 2021 and 2022. Anyway, you can look at the above normal probabilities, the below normal probabilities, and it's just like we discussed in here in these rectangles. And say, for example, in this case here above Cuba, in the right plot, there's a 20% probability of above normal rainfall, a 35% probability for normal rainfall, and a 45%. All of these numbers add up to 100, or in this case, 99, if they're all equal chances. And you can see where the highest probability fits the category. So next, they also offer a temperature and drought outlook. Same thing. Your temperature statistically formed forecast where your probabilities for each different category above, normal, below are given. And the drought forecast is given by concerns of drought, either drought watch, drought warning. Again, these are statistically driven. And they also offer rain-related statistically driven forecasts. In this case, these are number of wet days, the number of 7-day wet spells. How many 7-day wet spells do you have? Very wet spells do you have per season? How many 3-day extremely wet spells do you have per season? Again, I'm not going to go into detail about this because we could chat for 30 minutes. My point is, if you're involved in agricultural applications, then this stuff might be valuable to you. For example, the number of wet days. Is that important? Is for planting. Also, dry spell outlooks. We talked about temperature. We talked about rainfall, and of course, dry spells are critical for agriculture as well. They could be obviously detrimental. So there's also a forecast where the CNH provides a probability of having at least 3, and also a max number of 7-day dry spells. Again, I'm saying this not to go into detail, but just to inform you that these products are available, ready for you to download and interpret. And it provides a regional, a climate outlook newsletter for the region, and available products from their website include outlooks, dry spell outlooks, heat outlooks, precipitation outlooks, temperature, wet day and wet spell outlooks. Here's the website. So these again are valuable tools. And your National Weather Service provides very similar information at the national scale. Here's, for example, in Belize, they provide a deterministic and a probabilistic seasonal forecast. You can see here it's millimeters of rainfall on the left. On the right, it's the tercile above normal, normal, and below normal category. National Weather Services also provide bulletins. For example, here's the Dominica Climate Newsletter, the Jamaican Agro-Met. A lot of resources available. I think this is the last slide. It is, okay. And I'd like to open it up to questions if there's time, or we can move on. But
yes, there's
again,
time.
emphasizing information availability and interpretation. Okay. Okay.
Debbie, I have a question. Which one, more than a query, with your experience, how will you recommend us to manage the information, to have a holistic approach when we making decisions? Because sometimes persons come to us requesting an information that is very tricky, but if we combine different ways of seeing the information, we could get with something very close. What is your experience on that? Can you advise us?
Okay, so my interpretation of your question is that it can be sometimes overwhelming and it requires bits and pieces to be fit together. So let's take, for example, the regional information versus the national information. The regional information will provide outlooks for a larger area. Now, for example, in the Windward Islands, provides information for Dominica, Barbados, St. Lucia, St. Vincent, Grenada, for example, and that'll give a regional outlook. Now, forecast for Barbados is going to be the same for the forecast for St. Lucia. But what it does mean is when you average across the region, you will get to look at the national outlook products, to look at the national forecast for rainfall and temperature, and put that into context with the regional one. So you never want to just rely on one. So they kind of fit together, for example. And if you have access to your rainfall information and then you forecast from the CIMH, for example, if the rainfall forecast is higher than normal, but the wet day forecast is lower than normal, or what it might tell you is that while it might rain more than normal this season, the rain may fall on fewer days than normal. So you'll get fewer days of rain than normal. So you can combine multiple pieces of information to derive a meaningful interpretation. I hope this answers your question. But
yes, it's excellent. This is what I wanted people to get, that it's not just go to one. You still have to combine to be secure.
Exactly, and that's a great.
Okay, Dr. Allen, we also have another question.
Yes, this is about the. Okay.
Yes, how significant is the forecast for doing?
Okay, so this is a. Yeah, now here's the key point. He says on the micro level. So this is a scale. Not advisable to use large scale or coarse scale forecasts for fine scale applications, right? So for example, would I use a seasonal forecast for a region to drive the input for a micro level crop model for one section of an island? Consistent. So what I would recommend is that your local forecast or the local observation from a specific weather inform these types of micro scale needs.
All right, Dr. Allen, just for emphasis, just to repeat what we should not do, and what we should do.
Okay, so what's not advisable, and you can see here, I'm speaking in terms of more probabilities. I'm not saying what you should and should not do. Maybe I've been well trained, but what is not advisable is to use large spatial scale coarse information to drive micro scale fine inputs. So if your interest is doing a micro scale crop model, advisable to drive that model from a single weather station closest to that location and not a regional. Okay.
All right, thank you, Dr. Allen. George, please.
Thank you, Melissa, for acknowledging me. The presentation is very interesting. There are parts of it which were very sketchy in terms of the audio, but we really did get the gist of it. I'm just picking back on your response, Teddy, with regards to my question on doing the crop modeling for the micro level. Your response is that you should use pretty much the information from the local forecast. But even that too is, the pronostics are vague, and not necessarily so with regards to the day-to-day weather, but the general forecast in terms of the longer period. So you'll be told that the year would have less rainfall, and really and truly it doesn't. Of course, the prognosis can be wrong. You articulated that clearly, Dr. Teddy. But then, if you want to use the information, which is very generalized for a large surface area like Belize, I want to identify with this particular country, for example. The reports would say something which goes like this: generally fair weather will prevail. Showers will be isolated mainly along the coast and in inland areas. You know, have a drop of water anywhere in the inland areas. Then along the coast, you might even see it. It might be over the sea itself, and it might be probably in the night. So isolated showers, generally fair weather, those type of prognostical information sometimes can be that vague that one cannot justifiably do a model, perhaps on a year-to-year or on a 6-month basis, to ensure that, you know, an informed decision is taken with regards to, you know, the type of crops and when you want to plant them. You know what I mean? Thank you.
Yeah, I understand. Yeah, the confidence in the forecast and the ability is going to come into question, but yeah, definitely.
Okay.
Did I see somebody raise their hand?
Yes, Shanae. Shania. Shania, do you still have a question? All right, in the meantime, we have a question from Sam. The weather information, looking at temperature and humidity from a mobile app for a local area, is different from a device situated at the location. Can this be explained, and which one should be taken as true?
That's interesting. You know, I don't have any experience in that. That does each other like it should be the same. So why is the mobile app? Oh, unless that's okay. Unless that's referring to a mobile app from an external at that location. If that's the case, then the observation at location is always the truth, right? And the mobile app is providing a best estimate forecast for that location. That would be my interpretation of that question.
Sam, did you want to clarify? I saw your hand up.
Yes, good afternoon. Right, so the mobile app information is coming from weather.com, and I normally cross-reference that information with a device that I bought from Amazon, which gives you an indication of the indoor and the outdoor humidity and temperature readings. So normally it's normally way out. So like in the morning when it's cooler and when the humidity value is high, there's like at times a 10% difference in the humidity reading between the device situated at the location and the mobile app. Similar with the temperature, it's the differences are not so great, but you will get like a degree or two difference between the device and the information from the mobile app. So I just wanted to find out, which one would be taken as true. Is it a case that the device that I have at home is not calibrated? Do I assume it is calibrated or what? So I just wanted to get some further clarification on that.
Yeah, okay. So my guess is that the mobile app, weather.com, is providing a generalized forecast for an area. And you're looking at your results from a specific location. So almost never will, because your specific location is going to have constraints that are specific to you that will be averaged out through the weather.com. Now, weather.com or your coordinates, but it's never going to have information at every single dot on the earth. Instead, it averages it in average of your location that's closest to that area. So that's what's providing that difference and not necessarily any calibration issues.
Okay, thank you, Dr. Allen. Thank you to everyone. At this point, we are going to take a 5-minute break. We'll resume in 5 minutes at 10:42 a.m. and we will get into module 7. Thank you, everyone.
Okay, Melissa, may I ask you a quick question? Melissa.
Yes, sure.
Audio, I might have, how bad is my audio?
Yes, it goes in and out.
Okay, I'm going to bring down, connection, and maybe I can do the presentation on my laptop, but speak to my tablet. So I'm going to go try that while we're in break. Okay.
Great, thank you.
Melissa, Sheena had a question. Her audio was giving problem. Can you give her just a few minutes? She's from the Met office, so she would just want to make a point.
Sure. Shanae, are you still with us?
Shania, we not hearing you for some reason. No. We still not hear you.
How about now?
Yes, now we're hearing you. Go ahead.
Okay. I was just responding to the comments made by Mr. Emmanuel earlier that in the case of Belize, the general forecast is actually intended to be general, to just give persons an idea of what, depending on location, the weather is expected to be. But for agriculture and other purposes, there's other different types of forecasts that are produced. So we do have a separate Agro-Met forecast that includes for a particular day an estimated rainfall amount that is done on a finer scale, and also a seasonal and monthly forecast that are prepared. So I don't think it's best for you to use the general forecast to make a decision on for agricultural planning purposes. It's best to use the other types of forecasts and also the Agro-Met bulletin that is available. And then in terms of the general forecast, we are currently working on preparing a more area-specific forecast. For instance, give more information on township rather than just, like you said, along the coast. We are making general forecasts to be more specific to certain and towns.
Thank you, Chanel. Hi, everyone. Just to give Dr. Allen a little more time to get to his new setup, we will resume in 3 minutes. Thank you.
Melissa, are you able to hear me now?
Yes.
Okay, is this better?
So far.
Okay, I think I figured out a solution.
Okay.
So I am double manning 2 laptops. One's for volume and one's for the presentation.
All right.
So I'm hoping this is going to be better.
Okay.
Okay, I'm ready when you guys are.
You're ready. Okay, well, we're back. All right, Dr.
Okay.
Allen is up again, and hopefully it will be better this time. Thank you again for your patience. Dr. Allen, the floor is yours.
Okay, so let's see if this is going to work for me. Okay, great. So module 7/8. So we are going to look at the SPI as a drought monitoring product and understand what SPI means and why it's used and show you how you can access it. We're going to look at climate trends and discuss how climate index can be calculated. We're also going to look at a certain type of index called the NDVI, or vegetation index. So the objectives for this or these final modules are: 1, a successful interpretation of SPI values and maps, because these are readily available and often used throughout the region for drought monitoring and agroclimate applications. Successful interpretation of climate trends and indices, and also successful interpretation of NDVI vegetation maps. How's my audio now?
Good so far.
Oh, good. Okay, excellent. Okay, so we'll switch slides. Oh, great. Okay, so let's talk about this thing called the Standardized Precipitation Index. Let's see here. Hold on one. Okay, so the SPI characterizes drought on a range of timescales. On short timescales, the SPI is closely related to soil moisture, while at longer timescales, the SPI can be related to groundwater or reservoir storage. It quantifies observed precipitation as a standard departure from a selected probability distribution. Okay, what does all that mean? Why am I telling you this? It sounds complicated. Okay, let me break that down. All I want to tell you is that the SPI is a drought product. It can measure drought on various timescales. And if you look on the top left, it's driven by observations. These are just daily rainfall observations. But you can see how some days are more than others and some days are less. And if you look at the rainfall, any sort of rainfall observation, you will know, or you will see, that it tends to rain less than rain more. You have more days without rain than days with rain. So that's often called a gamma distribution, where you get a higher number of low rainfall days, okay? So what you do with the SPI, you have to convert it to a gamma distribution, and then you convert that to a different distribution, and then you can take your anomalies. This does not pertain to you directly. I just want you to know that there is a little bit of math that goes into here, but it's all driven only by rainfall. The SPI is a drought product that involves only the statistical interpretation of rainfall, okay? Nothing else. Moving on to the next slide, we're going to put SPI, the Standard Precipitation Index, into context of different types of drought. So in general, there are 5 different types of drought: meteorological, hydrologic, agricultural, ecological, and socioeconomic. And each of those types of drought are classified by a different time scale. So meteorological drought is a drought on a short time scale, where socioeconomic drought is a drought on very long time scales. So meteorological drought is related to rainfall amounts. Hydrological drought is related to water levels in reservoirs. Agricultural drought, as you can imagine, is related to the availability of water for crops. So we can use the SPI, or the SPI can be calculated for various timescales that will meet the needs of each one of these types of drought applications. So you can create the SPI from 1 month up to 48 months. Again, it uses precipitation only, and the SPI, we'll look at an example soon, but it characterizes drought or abnormal wetness at different timescales which correspond with the time availability, okay? So all of these different drought types can be analyzed in terms of different scales of SPI. Okay, so now we see we're going to calculate the SPI on 4 different timescales: a 1 month, a 3 month, a 6 month, and a 12 month. Now, why are we going to do that? Because I just said before that each of the different types of drought has a characteristic time scale. So you can produce a 1 month SPI that reflects short-term soil moisture. You can calculate a 3 month SPI, which is related to short to medium-term moisture. Oh, I see I got a question. Okay, so George wants to know what's the ecological and socioeconomic drought related to. These aren't necessarily related for us in the agroclimate world, but it has to do with economies, collapsing might be a strong word, but economies adversely responding to long-term drought. Okay, the ecological could be the availability of certain food supplies. The socioeconomic is a much macro scale, widespread economic impact. Okay, good. Okay, and then finally, we can look at, the 6-month SPI that's going to relate to stream flows and reservoir levels, and the 12-month SPI that it's going to describe shortfalls in groundwater amounts. So as you can see, each one of these time scales of SPI has its characteristic time scale of application. Okay. Switch slides. Okay. So the SPI can be looked at in terms of a time series at a specific location or a map over a larger area. So if you look to the left, this is just the SPI at one specific location, but here you can see in the top row, you have a 1-month SPI, a 3-month calculated SPI, a 12-month, a 24-month, and a 36-month. And remember, each one of these has its own application. Doesn't necessarily matter where this is or why I chose this. The point is, I just want to show you the different ways in which we can plot SPI different timescales and how they might look. Now, these rainfall anomalies that created this SPI, these are all taken from the same observation. So the 1-month SPI in the top is directly related to the 36-month at the bottom because it's the same location, same time series. And basically, instead of looking at 1-month variability, now you're looking at 36-month increments, okay? So if you look at the 1 month on the top left, you can see, okay, look, there are a lot of reds kind of near the far right of the time series around 2001 to 2010. And if you aggregate those 1-month reds into 3-month reds, or you aggregate them into 12-month reds, or 24-month and 36-month, then you start to see these block patterns in the larger 36-month, 12-month, 24-month SPI plots. Now, likewise, you can also see areas of positive values of green, so wetness. So the SPI isn't just describing the drought and the water deficit, it can also describe water availability. Now, remember on the left was 1 point. You can map each one of these points at one specific time on the right, and that's what we're looking at here. This is Spain. These are SPI values for a location in Spain. Sorry, not a location in Spain, for all of Spain, but it's only at one time. So the time series is going to give the SPI at one location over many, many months or years. And the map is going to give the SPI at one specific time, either 1 month or one season of a specific date. Okay. All right. Any questions so far? Move ahead. Now I'm going to introduce a deviation from the SPI called the SPEI. This is called the Standardized Precipitation Evapotranspiration Index. So recall the SPI used nothing but rainfall data. Now the SPEI let me back up for a second. The SPI has been in use for, I don't know, maybe 50 years. Lately, maybe in the past 15 years, the SPEI has been created as an enhancement for the SPI. So the SPEI came later, and it was a way to maybe improve the existing SPI. And the way it can be improved is by taking into account both rainfall and potential evapotranspiration values. So the SPEI captures the main impact of increased temperatures on water demand. So the SPEI is going to include temperature information and rainfall information. So I just like to show you examples of how this is applied. Here we have a map. This is somewhere in the Iberian Peninsula. So parts of Portugal, parts of Spain, but the color map is represented in kind of middle Spain. Okay, so this is just topography in this map. Now, below that, you can see there's a time series of blue, which is water flow towards this region, and then red, which is your SPEI, your 3-month SPEI. Below that is your 40-month or your SPEI 40. And now what you see, you have positive values above the line and negative values below the line, but for some reason, whoever produced this map chose to use red for both positive and negative values. So anyway, you can see from 1995 to about, looks like, sorry, 1965 to about 1980 or so, you had all positive values for SPEI, and then you had longer values of negative readings. So SPEI can be shown the same way as SPI. Now, if you look at the right sets of plots, the SPEI versus the SPI, now what you can do is you can compare what the SPEI would look like relative to the SPI at the same location, same period of time. So I've circled just this one area, but in 2003, you can see that if you just look at the SPI on the right, it's about -1. But if you look at the SPEI, that includes temperature, it's almost -2. So in this case, you're providing more detailed information. So with the SPEI, you're getting the plant's process of transpiration and evaporation that's represented by this term called potential evapotranspiration. And both are influenced by temperature, humidity, sunlight, and wind. So it's just an enhanced SPI product. Okay. Moving forward, these products are also available and archived from the CIMH. And as a reference, if you do access this and you use SPI and SPEI products for your decision making for agroclimate work, you'll see there are ranges. You have positive and negative ranges. So exceptionally dry is when your SPI is less than 2. Exceptionally wet is when it's greater than 2. And you can see it ranges from exceptionally dry to extremely dry, severely dry, moderately dry, and slightly dry and just normal. These definitions are fairly standard, and they're fairly standard within this range of values. So when you do access an SPI and SPEI map, you will see these values and they will be consistent. Okay. And again, here's the website if you do want to access these products and you haven't already. In addition, the CIMH provides not only just the SPI and the SPEI products, but they provide drought bulletins. That would be extremely helpful as well. And if you do want to access that, I'm going to give a very quick interpretation of some of the SPI and the SPEI products. Here you can see it's the SPI 12, SPI 1, in addition to the SPI 12 and 1. And remember, this is a different time scale. It's your 12-month scale and your 1-month scale. The 1-month scale is your meteorological information, just rainfall. And the 12-month is going to be related more towards drought. Okay. So here you have 2 different columns, a long-term 12-month column from July 2020 to June 2021 on the left, and on the right, just a 1 month, just last month or 2 months ago, June 2021. So if you compare the SPI and the SPEI 12s on the first column, you'll see, oh, they are a little different. Now look at the Guianas region. They're both blue, okay? Yeah, so they're both in terms of extremely wet to very wet, okay? So they agree there. Now, if you look at Hispaniola, when you include temperature information for the SPEI. Now, for that 12-month period, it's about the extremely dry to severely dry. Whereas in just the SPI, it's fairly normal. So you can see the differences between, I don't know if you can see my mouse moving, Hispaniola here in the SPI 12 versus Hispaniola here in the SPEI 12. So there are differences, okay? There are differences. Now, if you just look at the June, so just this one column, the 1 month SPI and SPEI, here they're a little bit more similar because you're just looking at one specific time when maybe the temperature wasn't as extreme. In this case, for example, you can see in in Cuba and parts of Jamaica that the SPI and the SPEI for that 1 month was in the wet category. Okay, so yeah, just some areas to interpret. Now, final thing I want to say about this is that these maps are all produced from individual weather stations at each country. Now you might be saying, well, how in the world do you get SPI, SPEI information in the middle of the Caribbean Sea? Well, wherever you don't have weather stations, the map is interpolated. So it's more confident over land areas than the water areas. It's just a graphical interpolation to fill in the voids. Now we're going to move on to looking at trends and indices.
Dr. Allen, we do have a question.
Yeah.
If we're able to take it now. For ET in the SPI, what is the model plant used?
Could you repeat that? For what? For
ET in the SPI, what is the model plant used?
I do not know that. I don't know the actual specifics of the physiology that goes into the SPI. I'm sure there are other experts with more of an agricultural expertise that could answer that. So unfortunately, I do not know that piece of information off the top of my head. Okay. So now we're going to look at move from the SPI to looking at trends and indices. Okay, and you can look at the trends of the SPI, and the SPI is also an index, right? An index is an indicator, a sign or a measure of something. So the SPI takes rainfall, it statistically manipulates it to produce an index called the Standard Precipitation Index to have a meaningful representation for drought. Okay, so it is an index. With an index, you can plot the time series and also look at the trend. Okay, so here I've plotted the SPI for 3 different time scales, SPI 3, SPI 6, and SPI 12 at 2 different locations, Jamaica on the top row, St. Lucia on the bottom row. And here you can calculate the trend in SPI, which is represented in each plot. And let's just look at the SPI 3 for Jamaica and St. Lucia. The trends are negative 0.48 per decade or 0.36 per decade in St. Lucia. Now look at the SPI 12 trend for Jamaica. It's -2, so going down 2 per decade. That's a huge trend. Well, let's also remember that this time period, 2015, 2016, was very, very, very abnormal. That was a mega drought, a long-lasting El Nino, and that skews the statistics if you're looking at the trends in this time period. So it's important, if you analyze a trend, to look at the outliers. And if there are major outliers, then the trends may not be that meaningful. And that's what I wanted to show you in this case, right? So trends can be calculated from indices or an index. Now, you can also calculate other indices from rainfall and temperature data. And I want to say right here, all of these indices that we're going to look at on this slide, they are produced from a free software that the CIMH has trained every meteorological service in the Caribbean on how to use and produce. So you can, if you don't work in the Met Service, you can ask to see if they have produced these indices and if you can access them to aid in your decision making. Now, examples of some of these indices are annual number of days with precipitation greater than 50 millimeters. There are about 50 different indices that you can produce. The top middle one, the maximum annual 1-day precipitation total. You get a plot of that. You can also plot on the top right, the average annual daily rain rate on wet days. On the bottom left, for example, and this is Jamaica was on the top, St. Lucia on the bottom, the number of days contributing to heat waves. Bottom middle, annual mean daily mean temperatures. Bottom right, percent of days, blah, 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 blah. You get the point. The point is that you can make indices of almost anything given your temperature or rainfall data. You can also calculate trends. But let's dig into the details of just one of them, okay? How about we look at the bottom middle, the annual mean daily mean temperature for St. Lucia. So what does this mean? It means if you take all the average temperatures of that day and you average them for that year and you plot that value every year, this is what you get. And you can see in St. Lucia, the trend is increasing, okay? So this type of information can be used if you want to consider long-term changes in any sort of agricultural activity based on historical trends. Is it getting warmer? Is it getting wetter? Is it getting drier? Is it getting cooler? And if so, what does the time series look like? And what does that trend represent? Now, a final index I want to show you is called the Normalized Difference Vegetation Index, or NDVI. Has anyone ever heard of NDVI or used it before? I want to open that question up to the audience. Has anyone ever heard of NDVI or used it?
No.
Okay, so I got a no there. Okay, got a yes, good. Okay, some people are familiar with it. It's totally okay if you're not. I wouldn't expect it. But the NDVI is an index or vegetation index that describes chlorophyll content or the greenness of vegetation. So how in the world do you describe the greenness of vegetation? Well, that's done through a specific sensor that measures how sunlight reflects off the plant. And that sensor can be put on a satellite, or it can even now be put on a drone, which is pretty amazing. So it describes the difference between the reflectance of the near infrared versus the infrared solar radiation. So this is a little bit of too much physics, but basically if you look at this tree plot on the bottom, you can see the difference between what's going out in the near infrared versus the infrared is 42. And if you look at the right, what's going out in that one, it's 10, the difference in percent. So the smaller difference implies unhealthy vegetation. The bigger difference implies healthy vegetation, because healthy vegetation reflects a lot in the near infrared and reflects a little in the infrared. Again, look at the unhealthy. It reflects a lot in the infrared and less in the near infrared. And again, you have to have special sensors that measure this stuff, okay? So this can be very convenient because now we have a way to actually monitor the vegetation greenness from on the land. And I think from here, yes, one more slide, and then we're going to jump into an example. Here is a real application of using the NDVI. This is an example in Jamaica. Now, remember yesterday, if you will, we talked about rainfall and the annual cycle of rainfall. And some places had a bimodal rainfall pattern, which means there was an early peak and a late peak. In the middle of those peaks, there was a midsummer minimum, right? So this map here looks at how the vegetation responds to that midsummer minimum in Jamaica. And I've outlined here the parish of St. Elizabeth, which is considered the breadbasket of Jamaica. And if you look at St. Elizabeth here, you can see there's a high percent change, negative change in NDVI from the early rainfall season, say around May, to the midsummer minimum period around July. So here you can see, or you can ask yourself, how does your area respond to changes in rainfall? How does your vegetation respond to changes in rainfall? And you can do this using the NDVI. And Melissa, can you just remind me how much time I have left? Because I want to go through one example. How many? 15? Excuse me? 20. Okay, good. Thank you. So now I'm gonna stop my share. Oh, we got a question here. It says in Belize, there's an annual mapathon, and they're asking us to assist them to read the vegetation types. Any recommendation? Okay, so are they asking you to produce it, or are they asking you to interpret it? Are they going to give you something to interpret, or are they asking you to produce it?
They giving us something and they wanted us to interpret it, especially in area. They do in forest, but they don't have experience in agriculture crops. So they're asking us to work with the agricultural areas.
Okay, right. So would that be in relation to rainfall? How do these areas change as rainfall changes? Or are they just saying, hey, here's a map of a forest, tell us what it means? Because that might be a very different question.
Well, so far what they have is they have a satellite view, and they trying to determine what kind of crops or forest is there.
Oh, yeah, yeah.
So it's more to determine what is there. So
yeah,
they
exactly
could measure it in general.
So what you would have to do with that is what's called an image classification. So you would have to know, and you'd have to use some remote sensing software to do this. You would have to know a specific area, you'd have to know the vegetation of a very specific area so you could classify the rest of that map relative to that area. So it's called image classification. It can be done. It requires some expertise in the use of remote sensing software. I'm sure there are a lot of people in Belize that have that skill. It can be fairly common, especially in some meteorologists and some climatologists maybe, but if there's a remote sensing group there as well. So it's possible, just you got to have the right resources. Okay, so now, let's see, we got that. Okay, good. So now what I want to do, I want to jump into an example on how to produce your own NDVI map. Everyone ready to do this? So if you have access, yeah. Okay. So let's see here. Okay, I'm going to share my screen in a second. I'm going to go here. Okay. Give me 1 second. Okay. I'm going to share my screen. Let's see here, should be here. Oh, no, I don't want that. I want this. Okay. So now I'm sharing, I hope, my screen as it comes up. Okay, good. Let's see here. All right. So I want everyone to get on a web browser if you can.
And then in Google or whatever you use, type in NASA Giovanni, and I'll write that in the chat. Oh, good. Melissa put the link there. Thank you. So we're going to click on NASA Giovanni. This is going to bleed into the next module. I want to get you guys looking at these vegetation indices as a practical example. Okay. So if you click on NASA Giovanni, it's going to bring you to their webpage. Now, I've already logged into this because I was using this yesterday, but you may see a prompt. Let me go ahead and log out. Now, or actually, I should say, has everyone had a chance to go to this link before and actually register? I know Melissa had sent an email. Registration just means putting in your email and selecting a password. If you've done that, go ahead and log in. Okay. So has anyone, or you can follow along with me. Okay, but if you have already registered, please log in. Has anyone registered? Okay. Okay, I'm in the essence of time. Oh, great. A couple of you guys have. Great. So everyone, if you have registered, have you logged in already? Okay, good. So follow with me. We're going to go on the left here and see where it says measurements. Click on that triangle that says measurements. Okay, click on the triangle that says measurements. And now if you scroll down, you will see eventually something that says vegetation. Do you see vegetation there? Click that box. It says vegetation. Let it do its thing. And now scroll all the way back up. And here you will see all of the satellite products from NASA on this portal that are related to vegetation. And look at this. We have NDVI. So we are able to access satellite-based NDVI and map it based on our own particular needs. Now, if you look in detail here, you'll see if you click on NDVI, it highlights in blue. And here's just some data. The source is from the MODIS Terra satellite. It's a monthly value, and it's calculated at every 0.05 degrees. I'm going to mute because there's a big bus coming. Hold on one second. Okay. And the earliest you can retrieve this data from the satellite is February of 2020. And the latest you can get it is from July of just last month. So let's do this. Now everyone's checked the checkbox at NDVI. Okay. Now we're going to go up here at the top left, and you're going to select a plot. We're going to select time average plot. Now you have all these different options. You can make a time series of NDVI as specific location. You can look at an animation. You can look at seasonal averages. But for right now, we're just going to do a simple time average. Okay. Now, it says here, it won't let me because I want to make a time average from 2000 to 2021. No, that's way too much data. So what we're gonna do, we're gonna restrict our ranges. For this simple case, because it's just an example, I'm gonna type 2021, and I'm gonna go to June 06. Oops, sorry. 06, and I'm gonna go to June. So this is just gonna be a time average from June of 2021, just 1 month. So my ranges are June 2021 to June 2021. And now it's gonna ask me, well, where do you wanna do the time average? So I'm gonna select this box here, and I get to draw a map. Now, I'm gonna caution you to not draw a large area at first for this purpose, because a large area is going to have a lot of data, and it's gonna take maybe a minute or two to process it on the website. So because of that, I'm going to choose a very small area, and you can choose any small area you want. I think since we've got colors from Belize here, I'm gonna go to Belize. Never been there, this is my first time, I'm gonna go to Belize. So I'm just zooming in, the map will redraw. And once I'm happy with the area that I wanna look at, there's Belize right there. Now I click the top button here, just click and drag, and I'm just gonna click a little section of Belize just for a demonstration purpose. And then what you can see, I'm gonna X out of this now. That box does now have these coordinates. I'm doing a time average of NDVI for that one particular month. Let's plot the data. I push plot the data. It's doing some work for me. I like that. Blue bars are always good on a website. And lo and behold, there is my NDVI, my average NDVI for Belize, that section. I'm going to zoom out a little bit. There. Okay. Now these values are very high. Of course, it's summertime. I'm just going to show you real quickly. I can change the colors a little bit to get some options. I'm gonna move my max. So NDVI goes from -1 to +1, but just to get the colors to look a little different, I'm gonna put 1.4 as my maximum. Keep this color range. I don't have to smooth it. I'm gonna replot it. I'm just looking at some graphical changes here, that's all. It's replotting it for me. Some variability, but perhaps in this example in Belize, I don't get much variability in vegetation. Maybe you can say, okay, it might be a little stronger towards the south, maybe a little weaker towards the north of this box. But yesterday, I did this for Jamaica, and I'm just going to show you some of my results in the essence of time, what it looks like for Jamaica. So here, this was my time average in NDVI for July of 2016. And you can see a couple things. It tends to be more green up in the northwest and the southeast. Now, don't let this fool you. There's low NDVI right here because this is Kingston. This is an urban area. Okay, so of course you're not going to have high vegetation there. So you can do area average maps. Now, I just did 1 month here. I could have done an area average for an entire year, but I just did 1 month. Now, I can take that area average, I can take all of Jamaica and say, hey, look, if I take all of Jamaica and I average all those values to 1 point, how does the NDVI vary from July of 2016 to July of 2018. And this is what you get. You can see there's a peak in NDVI in the late summer and a decrease in NDVI in the midwinter, late winter, early spring, and then the cycle continues. Now, I also did a longer time series, and here, starting from 2014 all the way to 2018, you can look at the variability of NDVI for that same area in Jamaica. And so where you can see, yes, you have a peak every summer, but sometimes, in this case, the peak was higher in 2019 than it was, say, in 2015. And you could also say, look, in 2015, the summer NDVI for the whole average area was much lower than the following summers, meaning there was definitely some sort of drought activity. There was a strong El Nino year. And yeah, you can get as long of a time series and choose your own area to produce this as well. And the point of doing this is to look at your vegetation variability and relate that to your temperature and rainfall variability. As an agro-meteorologist or Ministry of Agriculture, anyone involved in agriculture, you can say, hey, are there times of the year that are higher vegetation than lower vegetation? And might that help my decision making on what and when to plant and how to plant and so forth, right? Now, final, let's see, oh, that was the last one, yeah. So final one I can show you that you can do here. You can, in this NASA Giovanni, you can make an animation. You can see how your NDVI changes. Let's see that there's a little bit of a lag. I don't think the animation's really showing up here because the internet connectivity. Let's see here. Oh, there we go. Still, yeah, there's a lag in the internet, so the animation's not quite working. So anyway, I'm going to end here. Open it up to questions. Okay, so we have just a few more minutes. And just to summarize, the NDVI is just one index to use to look at the relationship between weather, climate, and vegetation. Might somebody access that? Was that interesting, or did that have value, and the time series of NDVI have value? It's okay if it didn't.
Myra?
This is very interesting. I think as the time gets short, it would be nice if you give us like a location you want us to do, and we could do as an exercise and send it to you, because I think everybody would like to try it with time, no? Because there's so much information in such
Definitely.
a time. But I'm not sure it's a value for everybody. For us, it's amazing.
So what I can do is I can draft in the next day or two a little tutorial, and I will send that to Melissa, and she can send it to the group, and then you can try it and see if you have questions and how to produce your own NDVI time series and so forth. And yeah, you can follow with me directly. I recognize this is just scratching the surface. We just had a few minutes today. My whole point was just to expose you to things and not necessarily expect you to become an expert on it. I just want you to know what the available resources are, how to access them in case you need to use them in the future.
Yeah, but this is something we need to learn how to use, because all of us will have, in many cases, have to report, and this kind of information that you want, we have to report. So I will encourage that, yes, I will keep saying part 2 of this, and send that exercise, because a lot of people have to try themselves, and we have to get our hands on it in order to practice, and then we will know where we having problems to implement it. But it's excellent.
Absolutely. And, you know, I want to be the first to volunteer if there's ever a need to have a 3-day workshop on remote sensing vegetation tools or how to produce more of these indices in detail, I would be more than happy to assist with that. But yeah, I will come up with a tutorial. Give me about 48 hours and to produce it, and we'll get it out, and we'll go through it together. And don't forget, I don't want the NDVI to overshadow the SPI and the SPEI products as well, and the other seasonal products from the CIMH and the your national services. They're just as useful. In fact, what would be interesting is to look at the time series of SPEI and vegetation at one location to draw any sort of relationships. And you could even look at it.
I was talking about the whole thing. Give us chance to try to use the holistic approach for everything, and
perfect.
You'll be able to tell us, okay, you need to improve this part. You could do this. That is the kind of information we understand, but there's so many tools, so many things, and so much information.
Yeah.
No?
Absolutely. You're right. Absolutely. So I hope I didn't overwhelm you. I just wanted to give you a little, like a little buffet.
Yes, exactly.
Okay, thank you so much, Dr. Allen. Thank you to all the participants who are so eager to see what else is available at their fingertips. So thank you very much, Dr. Allen, for your presentation. And that wraps up our core training modules for today. I will now hand over to Dr. Spence for closing remarks. Please don't leave us yet. We also have our assessment to do thereafter. Thank you.
Thank you, Melissa. Teddy, thank you for that really interesting stuff there. Yes,
you're welcome. And I just want to say thank you all very much for your patience with my technical difficulties on both days. I definitely didn't plan that, but I know it can be frustrating as a participant, so I'm very appreciative of your patience.
Right. So yes, we've come to the end of the 2 days of workshop. And I'd like to thank you, the participants, immensely for your patience where there were glitches. And of course, even with some of the material that might have been a bit heavy. And we've heard, the need for supplementation of the material that has been provided, and we are more than happy to do that. I had deposited my email in the chat so people can reach out to me so we can organize sessions, small groups, individual, whatever the case is, so that we can assist you further. Teddy has also expressed his willingness, and I'm sure Donovan as well would be happy to assist. Thank you for participating, and I hope the exercises were at least 2 days of training were beneficial, and there is scope for improving on this with the training manual to come. We're expecting to wrap that up by the end of this month, so that you can look out for that. That will also have some resources where you can access additional information and so on. To the presenters, Teddy, Aisha, Joel, unfortunately Donovan wasn't here, but I know he had worked along with Joel and Aisha in preparation for those nice pieces yesterday. Teddy, Melissa, who's working in the background organizing things, and also for the large part controlling some of the traffic during the training. Really appreciate the support. Special thanks to the IDB, Climate Investment Fund, UE, CARDI, for making this training possible, through whatever support. Mrs. Harris, we've had a couple of conversations and so on. All of those are appreciated in helping to make the workshop, the way it is. I hope that participants leaving here today will not wait too long before trying to dive into some of the things. I know that the presentations will be made available while we try to finish up the training manual. So don't wait too long. Look back through some of the things, keep it fresh in your minds, and that way you stand to benefit the most from what has been delivered over the past 2 days. We have a final assessment exercise to administer, and Melissa will probably send that out in the chat soon if she hasn't already. And once that is complete, then you are free to exit the meeting. We will be presenting certificates as soon as we have gone through the assessment exercises, because there was one yesterday and then there's a final one today. So we will be in touch with participants in the coming days. Please remember to stay safe, especially with us having, another spike in this COVID thing. Social distance, sanitize, and your mask, please. Vaccinations for those who are so inclined. But stay safe, and we will be in touch as we hope to assist you further in your various areas. All the best. Thank you.
Thank you, Dr. Spence. Yes, the assessment is now available in the chat. We'll be on for another 15 minutes or so to give you some time in the event you may need to re-access the link. anyone is needing more time, please just let me know. I know there's one other person who has asked for more time. If there's anyone else who needs more time, please let me know.
Bye, everybody. Thank you.
Take
All
care.
right, thank you very much as well, Maria. Have a good one.
Hello, Melissa. George here. Is there any specific reason why we should stay online on the call?
No, we were just allowing for persons who would still need some time or may have internet issues and may need to be resent the link. But yes, the session has ended.
Okay, thank you very much, kind miss. I can say from my end, we really appreciated the sessions, and well, we kind of look forward to maybe the next one, yeah?
Great, great. Thank you.
All right, Mr. Emmanuel, thanks for now.
Thanks, that's thanks. And you can refer to me as George. Everyone refers to me as George. We don't have any Mr. Emmanuel, Mr. George thing with me. But yeah, thank you so much, guys. I really appreciate it. And for all the other colleagues who were on too as well. Thank you so much.
Thank you. Thank you very much.
Have a good rest of the day.
Thanks, you too.
All right, we'll give just a few more minutes and then we will sign off. Okay, Dr. Spence, we're going to close now and save the recording.
So go again.
We're going to close now and save the recording.
All right then.
Okay, thank you, everyone.
All right, thanks. Yeah, man, thanks.